Hi, welcome to Last Day on Earth. Where are you listening from tonight? And what time is it where you are? Maybe you're in bed, letting the day fade. Or maybe you're out on a late walk under the stars. However you've arrived here, I'm glad you're with me. Tonight we begin a journey into a question that feels as old as the dinosaurs and as urgent as tomorrow. What if a meteor falls again? Could humanity survive? Together we'll explore what happened when the sky once fell, how we watch for threats today, what science tells us about the risks, and what it might take to endure if the unthinkable happens again. It's a story of danger, but also of resilience, of fear and of hope, of how fragile our world is, and how strong we can be when we face it together. So settle in, let your mind slow down, and let's look up at the sky and forward into the future. Chapter 1. The sky once fell. 66 million years ago, Earth was a world filled with giants. Dinosaurs ruled the land, some as tall as buildings and others no bigger than a modern bird. Herds of triceratops moved slowly across open plains, chewing through ferns and cycads, while sharp-toothed raptors darted through the undergrowth. Quick, coordinated, and deadly. Enormous sauropods, heavier than any machine humanity has ever built, swung their necks like cranes above the trees, eating constantly to fuel their massive bodies. Overhead, wings stretched wider than buses as pterosaurs glided across skies that were humid, oxygen-rich, and warmer than ours today. The oceans were just as busy, filled with giant reptiles like mosasaurs and plesiosaurs, and spiral-shelled ammonites drifting in the shallow reefs. It was a thriving planet, loud and alive in every direction. For over 160 million years, the dinosaurs had endured. Through climate shifts, through continents drifting apart, through predators and prey, constantly evolving in an endless arms race, they had become the masters of Earth, the most successful lineage of large animals the planet had ever known. To live in that time was to witness what seemed like permanence. But permanence is fragile, and the illusion of forever can be broken in a single instant. Far away, in the cold reaches of space, a rock drifted silently. 10 kilometers wide, it was not impressive compared to planets or stars, but its potential energy was immeasurable. It had been traveling for millions of years, nudged gently by the gravity of Jupiter, pulled slightly off its path until, finally, its orbit crossed ours. From the perspective of Earth, there was no warning. The dinosaurs never saw it coming. They had no telescopes, no language, no idea that anything beyond the sky even existed. One moment, the world was ordinary, filled with the routines of hunting and grazing and flight. The next, the sky lit up with a streak of fire. The asteroid struck the shallow seas off what we now call the Yucatan Peninsula. It entered the atmosphere at more than 20 kilometers per second. The air in front of it compressed and heated to thousands of degrees, igniting forests before the rock even touched the ground. When it hit, the energy released equaled billions of nuclear bombs. In the first second of impact, an enormous crater opened in the crust, nearly 180 kilometers wide. Shockwaves raced across continents, traveling faster than sound, toppling forests thousands of kilometers away. Water displaced by the strike sent tsunamis rolling across the oceans, waves taller than skyscrapers swallowing coastlines. The air itself turned into fire, scorching everything exposed to the open sky. Any living creature within hundreds of kilometers was annihilated instantly. But the true devastation did not end with that first day. The impact vaporized immense amounts of rock and sulfur-rich minerals, launching them into the upper atmosphere. Molten droplets rained down globally, heating the surface enough to ignite forests, even half a world away. Dust, ash, and aerosols spread through the stratosphere, forming a shroud that blocked sunlight. For days, then weeks, the planet dimmed. Plants withered, starved of light. Photosynthesis faltered. With no plants to sustain them, herbivores grew weak. With no herbivores, predators fell soon after. The collapse was ruthless, total, and inescapable. Temperatures dropped dramatically. A sudden winter imposed on a world that had been lush and warm. Acid rain fell from the sky, poisoned by chemicals released during the impact. The oceans, too, turned against their inhabitants. Plankton, the foundation of the marine food chain, died in the darkened waters. With them went ammonites, many reptiles, and countless species that had thrived for millions of years. In the space of a geological blink, 75% of all life on Earth was gone. And yet, life did not end. Small creatures endured in the cracks of this broken world. Mammals, mostly tiny and nocturnal, survived by burrowing and eating whatever they could find: seeds, roots, insects. Crocodiles lived on, hiding in rivers and lakes, their slow metabolism helping them withstand famine. Birds, descendants of small feathered dinosaurs, persisted where their larger relatives fell. These survivors would inherit the Earth, slowly reshaping the ecosystems left behind. From them, in the far future, would come us. When we look back on that day, we see more than just destruction. We see how fragile life is when faced with forces far beyond its control. The dinosaurs ruled Earth for 160 million years, and still they were undone in a single day. But we also see resilience. Life did not stop. It bent, it broke, but it did not vanish. Out of the ruins, new forms flourished. Mammals expanded into niches left open, evolving into creatures that would one day learn to walk upright, to build fire, to look up at the stars, and to wonder about rocks drifting in the dark. The Chicxulub impact, as scientists call it, is written into the rocks. A thin layer of clay found all over the world, rich in iridium, a metal more common in asteroids than Earth's crust, is the fingerprint of that catastrophe. In Italy, in New Zealand, in North America, you can find this same scar in the strata of stone. It marks the boundary between the Cretaceous and the Paleogene, a line between two worlds, one of dinosaurs and one of mammals. Every time we touch that layer, we touch the day the sky fell. And when we imagine it, we can't help but look at ourselves. If it happened once, it could happen again. The sky does not promise safety. Meteors still drift in space, countless fragments circling the sun. Most are harmless, burning up in the atmosphere as shooting stars. Some are larger, like the one that exploded over Siberia in 1908, flattening forests in an instant. A few are truly dangerous, mountain-sized bodies that, if their orbits cross ours, could deliver devastation, not unlike the one that ended the age of dinosaurs. The question is not whether Earth could endure. It has before, and it will again. The question is whether we, fragile as we are, could. Unlike the dinosaurs, we have tools they never had. We can see the sky with telescopes, track the paths of asteroids, even imagine nudging them aside with spacecraft. But still, when we think back to that day 66 million years ago, when fire rained from the heavens and darkness fell across the globe, we are reminded that survival is never guaranteed. It is something we fight for, prepare for, and hold carefully, because the universe is vast, and we are small. The sky once fell, and life changed forever. It may fall again. The only difference is that now, for the first time in history, one species knows it, and can choose whether to watch or to act. Chapter 2. What meteors are. When we talk about meteors, most people picture a streak of light across the night sky. A quick flash, a shooting star, here 1 second, and gone the next. But that little streak is only the final act of a story that has been unfolding for millions, sometimes billions of years. To understand whether we could survive if a meteor fell again, we first need to know what these things really are, where they come from, and how they move through space before they ever find us. The first thing to clear up is the language. We tend to throw around words like meteor, asteroid, comet, and meteorite as if they were interchangeable, but they each describe something different. An asteroid is a piece of rock or metal, usually orbiting the sun, mostly left over from the birth of the solar system. Most of them live in the asteroid belt between Mars and Jupiter, where gravity trapped them 4.5 billion years ago, preventing them from ever forming into a planet. Some are small, the size of a car. Others are hundreds of kilometers wide, mountain-sized bodies that have been circling the sun since long before Earth had oceans. A comet is different. A body of rock and ice, often described as a dirty snowball. When comets swing close to the sun, the heat vaporizes their ice and dust, creating those long glowing tails that stretch across the sky. These are visitors from the distant reaches of the solar system, the Oort cloud and Kuiper belt. Places so far away they are almost unimaginable. Then there is the word meteor itself. A meteor is not the rock, but the streak of light it produces when it enters Earth's atmosphere and burns up from friction with the air. When you see a shooting star, what you are watching is a grain of dust or a pebble, sometimes no bigger than a fingernail, entering at speeds up to 70 kilometers per second, glowing briefly before disintegrating. If that rock is big enough to survive the fiery plunge and land on Earth's surface, we call it a meteorite. So asteroid in space, meteor when it burns, meteorite if it hits the ground, simple in words. But behind those terms lies a whole world of scale and danger. Most of the time, meteors are harmless. Every single day, Earth is struck by more than 100 tons of dust and small rocks. They arrive as a constant drizzle of light, invisible in the day, sparkling at night. You could stand outside on almost any clear night, look up long enough, and eventually you'd see one. They are so common that they are part of human culture. Ancient people watched them and made wishes, told stories about stars falling from the heavens. They had no way of knowing these streaks were cosmic debris, reminders that our planet is always moving through a field of rocks. But sometimes the objects are bigger. In 1908, over the remote forests of Siberia, a rock about 50 meters across entered the atmosphere. It never touched the ground. Instead, the pressure of air in front of it caused it to explode in mid-air, releasing a blast more powerful than 1,000 Hiroshima bombs. Trees were flattened across 2,000 square kilometers. Had it arrived a few hours later, it might have exploded over St. Petersburg. And the story would have been very different. In 2013, in Chelyabinsk, Russia, a smaller meteor about 20 meters wide detonated high above the city. The shockwave shattered windows and injured more than 1,000 people. That was just a fragment, a reminder of how even modest-sized rocks can shake human lives. Then there are the ones like Chicxulub, 10 kilometers wide, large enough to change the whole planet. These are rare, thankfully. They strike once every tens of millions of years. But when they do, the consequences are global, rewriting the history of life itself. Between the tiny dust specks that make shooting stars and the mountain-sized asteroids that end eras, lies an entire spectrum of possibilities. Some mean nothing more than a pretty sky. Others could level a city, flatten a region, or starve a planet. What makes them dangerous is not just their size, but their speed. At 20 kilometers per second, even a rock the size of a house carries the energy of a nuclear bomb. There is nothing slow about a meteor's fall. They are ancient travelers pulled in by Earth's gravity, falling faster than anything else we encounter. When they strike, they turn motion into heat, pressure, and destruction in the blink of an eye. Scientists spend their lives mapping these objects, with telescopes scanning the heavens, with radar, with spacecraft missions. We try to catalog every rock whose orbit crosses ours. Thousands are known. Many more are out there, waiting to be found. They are part of our solar system, part of the debris left behind from its formation. Reminders that creation is messy, and that Earth is not a closed world, but part of a larger, dangerous neighborhood. And there is something humbling about that. Every shooting star you've ever seen was once a wanderer in space. Some of them are as old as the solar system itself, fragments from before Earth was even born. They carry the fingerprints of ancient collisions, the chemistry of the early sun, the story of how planets came to be. In a way, they are messengers, Harmless in small doses, catastrophic in large ones. When you lie back and see a streak of light in the night sky, you're watching the smallest, gentlest form of an event that has, in other times, erased worlds. It is both beautiful and terrifying to think that the same process that makes a moment of wonder for us at night can, under the wrong circumstances, plunge the Earth into darkness. So when we ask if we can survive, if a meteor falls again, it's important to remember what a meteor truly is. Not just a star falling, not just a wish in the dark, but a rock from space, part of a family of objects that surrounds us all the time. Most are too small to matter. Some are big enough to frighten but survivable. A rare few are large enough to alter the course of life itself. They are not rare in space. They are rare only in time, and the story of Earth shows us that sooner or later, one will come again. Understanding what meteors are is the first step in understanding the risk. They are not magic. They are not omens. They are pieces of the universe, leftovers from the making of planets, sometimes gentle enough to wish on, sometimes violent enough to wipe the slate clean. Knowing this is not meant to frighten, but to ground us. We live on a planet that is not sealed away from space, but constantly exposed to it. Meteors are reminders of that connection. They are the quiet messengers of the cosmos, crossing our sky in silence, some harmless, some dangerous, all part of the same story. And as we continue to move through space, orbiting the sun year after year, we remain part of that story too. The question is not whether meteors exist. They always have, and they always will. The real question is what happens when the next big one comes. Chapter 3. The Everyday Rain. Every single day, without pause or warning, the Earth is struck by objects from space. Not just once or twice, but constantly, a quiet drizzle of material falling through our atmosphere. If you were to measure it all, it would add up to more than 100 tons of dust and rock every single day. Most of it is so small you never notice, but it is always there. We live on a planet that swims through a sea of debris, and shooting stars are only the most visible reminder. Think of the night sky. You are lying back, eyes adjusting to the darkness, and suddenly a streak flashes overhead. It's so quick you almost doubt you saw it. That's a meteor, but the rock that made it was probably no bigger than a grain of sand. Traveling at tens of kilometers per second, it burns bright for just a moment before vanishing. Nothing reaches the ground. All that's left is the memory of light, and yet those tiny flashes are part of something much bigger. Earth moves around the sun, like a car driving down a dusty road. Every year we pass through regions of space thick with comet debris, left behind when comets shed dust on their journeys. When Earth plows through those trails, we see meteor showers. The Perseids in August, the Geminids in December. The Gemets, sometimes producing storms of thousands of meteors an hour. These aren't random. They are cosmic calendars, written in fire across the sky. For ancient cultures, they were omens, messages from the gods. For us, they are a reminder of the solar system's restless activity. Most of the time, these meteors are harmless. The atmosphere is our shield, a blanket of air so thick that almost everything burns up before reaching the surface. Only when a rock is larger than a few meters does it survive the plunge. The rest, no matter how fast they come, are consumed in fire. Our sky is not just blue, it is a guardian. But the everyday rain is not without meaning. It shapes us in ways we rarely think about. Tiny meteorites that survive to the ground carry with them minerals older than Earth itself. Some hold organic molecules, the building blocks of life. There's a theory that much of the carbon and water on Earth, the ingredients for life, may have come from countless impacts during the planet's early years. In other words, without this rain of space debris, life itself might not have taken hold here. What looks like destruction is also creation. Still, every so often, the drizzle reminds us of its power. In February 2013, over Chelyabinsk, Russia, a rock about 20 meters wide entered the atmosphere. It was just one rock among millions, but its arrival was violent. It exploded with the energy of 30 Hiroshima bombs, shattering windows and injuring more than 1,000 people with flying glass. Fall from a rock too small to notice until it was already on top of us. Go back further, to June 1908. Over the Tunguska region of Siberia, a meteor, about 50 meters wide, exploded in midair. The shockwave flattened trees across 2,000 square kilometers. An entire forest laid down in seconds, scorched at the center, as if by the breath of some invisible fire. Had that same meteor arrived a few hours later, it would have detonated over St. Petersburg, and the story of the 20th century might have begun very differently. These events remind us that the everyday rain is not always gentle. Most of the time it's invisible, quiet, poetic. Sometimes it is devastating. And yet, compared to the age of Earth, they are still minor events, local catastrophes, disasters for a region, but not the planet. Humanity could rebuild, life could go on. The dinosaurs never had that luxury when their day of impact arrived. There's something humbling about this knowledge. We live beneath a constant shower of space, rock. We go about our days as if nothing is happening. But above us, every hour, fragments of the cosmos are colliding with our atmosphere. We're wrapped in a shield that burns them up, sparing us from their full force. And once in a while, when conditions are right, we look up and see them, glowing against the night. We call them shooting stars and make wishes, never thinking that they are reminders of a larger truth. Earth is not isolated. It is part of a system full of wandering debris. The everyday rain connects us to the wider universe. It is a thread between our world and the deep past. When comets and asteroids bombarded the early Earth, delivering water and carbon, it is a bridge to the present. When a meteor can still surprise a city and shatter 1,000 windows, and it is a warning for the future, because among the countless tiny grains, there are always bigger ones waiting. Most will miss us, some will not. So when you see a meteor streak across the sky, remember what it really is: a messenger from space, a fragment of creation, a reminder that Earth is never alone, never separate from the cosmos. The everyday rain is both beautiful and dangerous, both ordinary and profound, and while it falls constantly, almost all of it harmless, the possibility always remains that one day one rock will be big enough, fast enough, and unlucky enough to change everything again. Chapter 4. When rocks get bigger, most of the time, the sky's visitors are small. They burn up as streaks of light, gone in a blink, leaving nothing behind except wonder. But every so often, something larger arrives, too big to vanish harmlessly in the atmosphere, too energetic to be ignored. When rocks get bigger, they remind us that our shield of air, as protective as it is, has limits. And those limits have been tested in living memory. In the summer of 1908, a clear morning over Siberia was shattered by a flash in the sky. The event would later be called Tunguska. Witnesses described the heavens opening in fire. An object about 50 meters wide entered the atmosphere and exploded in midair, releasing a force greater than 1,000 Hiroshima bombs. There was no crater, because the rock never touched the ground. The pressure of the atmosphere crushed it before impact, tearing it apart in a fireball. But the destruction was enormous. Trees were flattened across an area of 2,000 square kilometers. At the center, trunks were scorched and stripped bare. Pointing outward like matchsticks laid flat, shock waves circled the earth, recorded on barometers thousands of kilometers away. For weeks afterward, skies across Europe glowed at night, bright enough for people to read newspapers outdoors. All of this, from a rock, no larger than a small building. If Tunguska had struck a city, the story of the 20th century would have changed forever. Millions could have died in an instant. Instead, by chance, it exploded over one of the most remote forests on the planet. The Earth was spared by geography, not by immunity. More than a century later, in February 2013, another rock arrived, smaller than Tunguska, only about 20 meters across. But this time over a populated region, Chelyabinsk, a Russian city of more than 1 million people, was just beginning its day when the sky lit up. Dash cams on cars captured the moment. A blazing white fireball streaking across the morning sky, followed by a blinding flash and a deafening shockwave. The rock exploded high above the city, its energy equal to 30 Hiroshima bombs. Windows shattered in waves across neighborhoods. Walls cracked. More than 1,000 people were injured, most by flying glass. And yet, incredibly, no one was killed. It was luck, timing, and the fact that the object broke apart in the atmosphere before it could reach the ground. These two events, Tunguska and Chelyabinsk, are reminders of the spectrum of danger. They were not extinction-level strikes. They did not plunge the planet into darkness, but they were powerful enough to flatten forests and shake cities. They were local catastrophes, and they are not rare in geological time. Rocks this size strike Earth every few centuries. That may sound distant, but on the scale of human civilization, it is uncomfortably close. Imagine if the Chelyabinsk meteor had entered at a slightly different angle, surviving longer before breaking apart. A direct hit on a city would have destroyed everything within kilometers. Imagine Tunguska arriving not over a Siberian forest, but over London, New York, or Beijing. The human cost would have been unimaginable. These events remind us how fragile our sense of safety is, how much depends on chance. What's most sobering is how little warning we had. The Chelyabinsk rock came from the direction of the sun, hidden in the glare. No telescope saw it before it arrived. No alert was issued. People looked up, saw the fireball, and only then realized what was happening. Even with all our technology, space can still surprise us. When rocks get bigger than the grains of dust we call shooting stars, they stop being background noise and start being threats. They carry the energy of nuclear weapons, and they do not care about borders, politics, or preparation. They are reminders that Earth lives in a shooting gallery, a place where small, medium, and large objects crisscross our orbit endlessly. But there is another side to the story. Events like Tunguska and Chelyabinsk have sparked new urgency in planetary defense. Scientists track thousands of near-Earth objects, building catalogs of their orbits, trying to predict their paths decades into the future. Missions like NASA's DART, which nudged an asteroid's orbit in 2022, are proof that we are not powerless. We cannot stop every rock, but we can prepare. The difference between survival and disaster is often not size, but time. If we see an object decades away, we can act. If we see it only when it enters the atmosphere, there is nothing to do but watch and hope. So when rocks get bigger, they become more than shooting stars. They become warnings. They are messages written in fire that tell us the shield of air is strong, but not perfect. Earth has been lucky, but luck is not a plan. We live under a sky that sometimes drops pebbles, sometimes drops boulders, and while the small ones remind us of beauty, the bigger ones remind us of risk. The lesson of Tunguska and Chelyabinsk is that civilization has already been brushed by cosmic danger. Twice in the last 100 years, the Earth has felt the weight of falling stone. Twice, we escaped with no global harm. But twice is enough to tell us this will happen again. The only question is when and where and whether we will be ready. Chapter 5. The Dinosaur Killer. 66 million years ago, the age of giants ended in a single day. For more than 160 million years, dinosaurs had ruled the Earth. They had survived climate shifts, volcanic eruptions, and the slow drift of continents. They were masters of their ecosystems, filling every niche. Huge sauropods stripping leaves from treetops, horned triceratops defending herds, swift raptors stalking prey, and flying pterosaurs riding the warm winds above shallow seas. The oceans swarmed with mosasaurs and plesiosaurs, ammonites and corals. It was a thriving, noisy, living planet. And then a rock from space arrived. The asteroid that struck was only about 10 kilometers wide. Compared to Earth, it was tiny. But what mattered was not its size alone. but its speed, traveling at more than 20 kilometers per second, it carried energy equivalent to billions of nuclear bombs. When it entered the atmosphere, the air in front of it compressed so violently that it glowed brighter than the sun. In moments, it slammed into the shallow waters of what is now the Yucatan Peninsula, carving out a crater 180 kilometers across. The name we give it today is Chicxulub. The impact was apocalyptic. Shockwaves tore through the crust. Earthquakes rattled continents, and tsunamis hundreds of meters tall raced across oceans. Forests ignited instantly, set alight by radiant heat. Molten rock and vaporized debris were blasted into the upper atmosphere, where they circled the globe and began to fall back down as firestorms. But even this devastation was only the beginning. The true catastrophe unfolded in the skies. Dust, ash, and sulfur spread into the stratosphere, forming a veil that blocked sunlight. Days dimmed into twilight. Weeks passed without warmth. Photosynthesis faltered. Plants starved first, and with them the herbivores. The carnivores followed soon after. The food web collapsed like a fragile chain. On land, in the seas, in the air, life stumbled. 75% of all species vanished. Ammonites disappeared forever. Mosasaurs and plesiosaurs were wiped from the oceans. Most pterosaurs fell from the skies. And on land, almost every dinosaur larger than a bird was gone. What survived were the small and the adaptable mammals. Most of them no bigger than rats, survived by burrowing, eating roots, seeds, and insects. Crocodiles endured, hiding in rivers, their slow metabolisms allowing them to outlast famine. Birds, the feathered descendants of small dinosaurs, managed to hold on, scavenging and adapting until the skies cleared. These survivors would inherit the Earth, slowly repopulating a planet left hollow by extinction. Out of them would one day come us. The Chicxulub impact is one of the most important events in Earth's history, and we know its story because the evidence is written in stone. All over the world, from Italy to New Zealand, geologists find a thin layer of clay, marking the boundary between the Cretaceous and the Paleogene. This layer is rich in iridium, a metal rare on Earth's surface but common in asteroids. It is the fingerprint of the impact, a silent record of the day the dinosaurs died. When fossils below it are full of diversity, fossils above it are sparse, dominated by survivors. That line is a scar written into the planet itself. The extinction it caused was not instant, but it was fast. Within a few years, ecosystems collapsed. Within decades, the great reptiles were gone. Compared to the vast timeline of life, it was the blink of an eye. This is what makes Chicxulub so haunting. It shows how fragile life can be when the planet itself is struck by forces from beyond. Dinosaurs had been secure for millions of years, but their fate was sealed in a single day. Permanence, it turns out, is an illusion. Yet there is also something strange and hopeful in this story. If the asteroid had missed, the dinosaurs might still rule today. Mammals may never have risen. There may never have been apes, no humans, no history, no stories, no us. The same rock that destroyed one world created the conditions for another. Catastrophe became opportunity, though only after devastation. It is a reminder that survival and change are woven tightly together. When we ask if we could survive, if a meteor falls again, Chicxulub is the example we cannot ignore. It is proof of what a large asteroid can do, not in theory, but in fact. It shows the scale of destruction that even one object moving fast enough can unleash. It also shows that survival is possible but not guaranteed. Life continued, yes, but most of it did not. The line between survival and extinction was narrow, determined by size, adaptability, and chance. We live with the knowledge of this past. We can walk into museums and see fossils from both sides of the boundary. We can hold in our hands pieces of rock that contain the chemical traces of that impact. We can look at birds in our gardens and know they are survivors of the same event that ended the reign of Tyrannosaurus. And we can look at the sky, knowing that meteors still drift there, that impacts still happen. and that Chicxulub is not the only one in Earth's long history. It was just the most recent giant. The day the dinosaurs died is a story both of destruction and of inheritance. We live in its aftermath. The forests, the oceans, the animals we know, all of them exist in part because of what that rock unleashed. The same force that can end worlds can also shape them, carving new paths for evolution, opening doors that would otherwise remain closed. That duality is part of why the Chicxulub impact matters so much. It was an ending, but also a beginning. And now, as the species that inherited the Earth, we are the first to understand what happened. We can look back across millions of years and see the crater, read the evidence, and tell the story. The dinosaurs never saw it coming. We can. That is our difference. And that is our chance. Chapter 6. How likely is it? When people hear about the asteroid that ended the age of dinosaurs, the first reaction is often awe, followed by an uneasy question: could that happen again? And if so, how likely is it? The answer is not simple, but it is one we can trace step by step, from the smallest meteors that visit us every day to the rare giants that alter the course of evolution. The Earth is not isolated. Every moment it moves through a solar system filled with fragments of rock and ice, leftovers from the time when planets first formed. These objects vary enormously in size. At one end are particles no larger than dust, drifting invisibly until they collide with our atmosphere. At the other end are asteroids, 10 kilometers across or more, enormous enough to collapse ecosystems and darken the skies of the entire world. Each of these has a different likelihood of colliding with Earth. Each carries a different scale of consequence. The smallest are constant. Every single day, more than 100 tons of dust and tiny rocks fall into Earth's atmosphere. They streak across the sky as meteors, harmless and often beautiful, the shooting stars that inspire us to make wishes. These will never endanger us. They are so common that they are part of the planet's rhythm, as natural as tides or rainfall. Rocks a little bigger, the size of a car, arrive every year. They too almost always burn up before reaching the ground. They can produce brilliant fireballs, sometimes even sonic booms, but they pose no true danger. They remind us of the universe beyond, but leave no scar. The real concern begins with objects tens of meters wide. A 20-meter rock is enough to flatten a city. A 50-meter rock can devastate a region. These events happen on the scale of centuries. Tunguska in 1908 and Chelyabinsk in 2013 are examples. Tunguska leveled 2,000 square kilometers of Siberian forest. Chelyabinsk exploded over a populated city, injuring more than 1,000 people with shattered glass. In both cases, humanity was lucky. The timing and geography spared us from mass casualties, but they show what is possible, and they remind us that such events are not distant myths. They belong to our recent past, and they will happen again. When the size rises into the hundreds of meters, the timescale grows longer, but the danger grows sharper. A rock half a kilometer wide could disrupt global agriculture and climate. Its impact might not cause extinction, but it could starve millions, fracture economies, and trigger wars over dwindling resources. These impacts are thought to occur once every few tens of thousands of years. That sounds remote, but it is a heartbeat in geological time, and humanity plans to endure for far longer. Then come the kilometer-class objects, 1 kilometer across, moving at tens of kilometers per second, carrying the energy of millions of nuclear weapons. A strike of this scale could collapse modern civilization. Agriculture would fail under months of darkened skies. Crops would wither in sudden cold. Oceans would acidify. It would not end life, but it could end the world as we know it. These impacts strike on average once every 500,000 years, rare enough that most generations will never see one, common enough that Earth has recorded many across its history. And finally, there are the true giants. 10 kilometers across or larger, Chicxulub is one of these. The odds of such an impact in any given year are almost zero. But over the course of tens of millions of years, the chance becomes certainty. These are the events that reset the planet, the ones that turn one age of life into another. Without Chicxulub, there may never have been mammals as we know them. No primates, no humans. The rarest disasters are also the most transformative. When scientists calculate these probabilities, they do not speak in terms of if, but when. Given enough time, every size of object will strike again. The only unknowns are timing and scale. Will the next century bring another Tungus, flattening a forest or a city? Will the next 1,000 years bring something larger, altering global climate? Or will the next few million years see another Chicxulub, rewriting the story of life itself? The universe does not schedule these things neatly. They are random, but inevitable. What matters most for us is the difference between the small and the large. A Tunguska-sized event would be devastating for the people in its path, but humanity as a whole would endure. A kilometer-wide impact would test civilization to its core. A 10-kilometer giant could erase it. The spectrum of possibility is wide, and the frequency falls as the size rises. The smallest are constant, the largest are rare, but all are part of the same family of risks. There is comfort in rarity. The odds of a Chicxulub-scale strike in our lifetimes are vanishingly small. You are more likely to be struck by lightning multiple times than to live through such a day. But comfort can breed complacency. The odds of a city-level event, like Chelyabinsk, are far higher. These could happen in any century, even in any lifetime. And while they may not end civilization, they could still end thousands of lives. This is why scientists watch the skies so carefully. Telescopes map thousands of near-Earth asteroids, cataloging their orbits, predicting their future paths. Most of the large objects have been found. None pose a danger in the next 100 years, but smaller ones, the size that could devastate a city, are harder to spot. Many remain undiscovered, hidden in the glare of the sun, or lost among the stars. Chelyabinsk was one of these. It taught us that surprise is still possible, even in an age of advanced technology. So how likely is it? The truth is that impacts will happen again. The everyday rain of dust never stops. The city destroyers return every few centuries. The civilization shakers come every few 100,000 years. And the world enders wait in the long stretch of tens of millions. The scale of time makes the odds feel both remote and certain. Remote for us as individuals, certain for Earth as a planet. What sets us apart from the dinosaurs is not just knowledge, but foresight. They lived in ignorance of the danger above. We can calculate it, model it, and prepare for it. The likelihood of impact is real, but so is our ability to act. And perhaps the measure of our survival will not be whether another rock falls, but whether, when it does, we are ready. Chapter 7. Watching the skies. Every night, as most of us sleep, telescopes around the world are awake. They sweep the heavens slowly, frame by frame, capturing faint points of light against the darkness. To most eyes, it looks ordinary, just stars frozen in place. But astronomers are looking for something else. The points that move, rocks, drifting through the solar system, some small, some vast, some passing harmlessly, some crossing Earth's orbit. Watching the skies has become one of humanity's quiet but most important acts of survival. It began with curiosity. For centuries, meteors were seen as mysterious signs, falling stars that carried wishes or omens. Only in the modern era did we come to understand them as physical things. Rocks from space, moving on predictable paths. And with that understanding came a new question. How many are out there? And which ones are heading our way? The answer is sobering. Tens of thousands of near-Earth asteroids have already been identified. They range from small boulders, a few meters wide, to mountain-sized giants, capable of altering the climate of the whole planet. The largest are tracked carefully, their orbits calculated decades into the future. Every time one passes nearby, astronomers refine its path, adjusting the predictions with precision. Most of these objects pose no danger, but some, small and still undiscovered, slip through the gaps. Chelyabinsk was one of those, a 20-meter rock that arrived unannounced in 2013. No telescope saw it until it exploded in the sky. That surprise was a wake-up call. Even in an age of satellites and advanced observatories, the universe can still throw a stone without warning. Since then, the urgency to find and track more objects has grown. Around the world, networks of telescopes are dedicated to the task. NASA's Near-Earth Object Observations program scans the skies from both hemispheres. ESA operates its own watch, part of what they call space situational awareness. In Hawaii, the Pan-STARRS telescopes capture wide swaths of sky, night after night, looking for anything new. In Chile, observatories perched in the desert air map faint objects with clarity. Even amateur astronomers contribute, reporting new discoveries to central databases. It is a global effort, because space does not respect borders, and watching the skies does not end with Earth. Spacecraft, too, are part of the defense. Missions fly past asteroids, measuring their size, shape, and spin. Some, like NASA's OSIRIS-REx, even bring back samples, tiny pieces of rubble, that tell the story of how these bodies formed. Each measurement refines our models. Each discovery helps us understand what we might one day have to face. Perhaps the most remarkable step so far came in 2022, when NASA launched the DART mission, Double Asteroid Redirection Test. The target was Dimorphos, a small moonlet orbiting a larger asteroid called Didymos. The goal was simple in concept, but daring in practice. Crash a spacecraft into Dimorphos and see if its orbit changed. And it worked. The impact shortened its orbit by more than 30 minutes. For the first time, humanity had deliberately altered the path of a celestial body. It was proof that if we have time, years or decades of warning, we may not be helpless. Still, time is everything. A rock spotted decades away can be nudged aside with subtle force, like a gentle push early enough to matter. But one seen only months before impact leaves us with few choices. This is why the search is relentless. Every rock cataloged, every orbit mapped, every faint dot tracked through the night sky is a small act of prevention. There is something poetic about this work. We stare at the stars not just for beauty, but for safety. Telescopes that once mapped galaxies and nebulae now also keep watch for stones that might undo us. Astronomers, many of them working in quiet observatories far from city lights, are guardians of Earth in a way the dinosaurs never had. Their vigilance is the difference between ignorance and foresight, and yet there is humility in it too. For every rock we have found, there are more we have not. Space is vast. The glare of the sun hides objects approaching from certain angles. The night sky, even with our best instruments, is never fully known. We can reduce risk, but we cannot erase it. Watching the skies is not about certainty. It is about giving ourselves the best chance possible. One day, perhaps decades or centuries from now, a telescope will find something moving across the stars. Its orbit will be calculated, refined, and the numbers will say what no one wants to hear. It is coming for us. If that day arrives, our survival will depend on how long ago we found it and how much we prepared. Until then, the search continues. The sky is full of wanderers, some beautiful, some dangerous. And each night, as most of us rest, others are awake, scanning, calculating, guarding. Watching the skies is not just science. It is our insurance, our quiet defense against the possibility that the past could repeat itself. The dinosaurs had no such watch. We do. Chapter 8. First line of defense. When people first learned that asteroids had ended the reign of the dinosaurs, the idea of stopping one seemed like pure fantasy. How could humans, a species barely capable of leaving its own planet, hope to deflect a mountain falling from the sky at unimaginable speed? For a long time, the only answer was, we couldn't. But over the last few decades, something remarkable has changed. For the first time in history, we are building the tools to defend our planet. The first line of defense is no longer just luck. It is preparation. The most important step is detection. You cannot stop what you cannot see. That is why telescopes around the world, on mountaintops and in deserts, scan the heavens every night. They watch for faint points of light that drift slowly against the fixed backdrop of stars. Each discovery is measured and tracked. Over weeks, months, and years, scientists calculate orbits, predicting where each rock will be decades into the future. Most objects are harmless, passing at safe distances, but a few are flagged as potentially hazardous. These lists are the first shield, knowledge. Once we know where an object is, the next question is whether it can be nudged. The concept is simple. If you push a rock early enough, you don't need to move it far. A shift of just a few centimeters per second, applied years in advance, can mean thousands of kilometers of difference by the time it would have reached Earth. It's like changing the angle of a long throw. The earlier you act, the bigger the effect. There are different ideas for how to deliver that push. The most straightforward is the kinetic impact, or crashing a spacecraft directly into the asteroid to alter its speed. This was tested in 2022 by NASA's DART mission. The target was Dimorphos, a small moonlet orbiting a larger asteroid called Didymos. The spacecraft, no larger than a vending machine, hit Dimorphos at more than 20,000 kilometers per hour, and it worked. The moonlet's orbit shifted measurably. It was the first time humanity deliberately changed the path of a celestial object. The lesson was clear. Deflection is possible. Another method is the gravity tractor. In this approach, a spacecraft would fly alongside an asteroid for years, using its own gravity to tug gently on the rock. The force is tiny, but over long time scales it adds up. The benefit of this method is control. Unlike a one-time crash, the pull can be steady and precise. It is slow, but if detected decades in advance, it could be enough. There are also more dramatic proposals. Some scientists have considered using nuclear explosions not to shatter an asteroid, which could create a rain of deadly fragments, but to push it aside with the blast of energy. Others imagine attaching giant solar sails or painting the surface of an asteroid white or black to change how it absorbs sunlight, altering its trajectory through a subtle force called the Yarkovsky effect. Each idea has challenges, but the point is that there are options. Humanity is not helpless, but all of these rely on one crucial factor: time. If we spot an asteroid only months before impact, none of these methods will work. It takes years for spacecraft to be built, launched, and reach their targets. And it takes years for small nudges to add up to big changes. The first line of defense, then, is not the spacecraft itself. It is the watchfulness that gives us decades of notice. The defense begins with the astronomers who scan the skies every night, adding faint dots to their catalogs, calculating their orbits with care. Still, there are gaps. We cannot yet see every rock, especially smaller ones that come from the direction of the sun, hidden in its glare. Chelyabinsk was one of these, arriving without warning. To close this gap, new missions are being prepared. NASA is building the ENEO Surveyor, a space telescope designed specifically to find asteroids, using infrared light to detect their heat. Others are proposing networks of smaller satellites that could watch the skies from different angles, filling in the blind spots. Every step we take now, every orbit measured, every mission tested, is rehearsal for the day when the alarm will sound for real. It may not happen in our lifetimes, it may not happen for centuries, but eventually a rock will be on a collision course. And when that day comes, the tools we build now will be the difference between helplessness and survival. There is something deeply human about this effort. For billions of years, life on Earth had no defense. Extinction came suddenly, without warning. The dinosaurs never knew the sky could betray them. We do. And with that knowledge comes responsibility. Watching the skies is only the first step. Learning how to act is the next. DART was just a beginning. A demonstration that the laws of physics can be bent in our favor if we are prepared. The first line of defense is fragile, incomplete, and untested in a real emergency. But it exists. For the first time in the planet's history, A species is looking outward, not just in wonder, but in self-preservation. And so our survival no longer depends on chance alone. It depends on vigilance, technology, and the will to prepare for a danger that feels distant until it is suddenly near. The first line of defense is not perfect, but it is real. And if the sky ever falls again, it may be enough. Chapter 9. If warning comes too late, attack the night sky, clear and quiet. When somewhere in a desert observatory, a telescope captures a faint dot shifting ever so slightly against the stars. At first, it is nothing unusual. Astronomers find thousands of such points every year. But over the next nights, its path is tracked, its speed measured, its orbit calculated. Slowly, the numbers align into a conclusion no one wants to see. The dot is not just passing, it is coming. The trajectory points straight to Earth. The date of impact is not far in the future. Not 50 years, not even 10. It is less than 1. The warning has come too late. At that moment, everything changes. Governments are told in urgent whispers. Agencies check and recheck the orbit, running simulations until the computer screens blur. And still the answer holds steady. Impact is certain. With decades of notice, humanity might have had options. With years, it might have nudged the rock aside. But with months, the time to deflect is gone. The conversation turns not to prevention, but to survival. Imagine how the news would spread. At first, the information would be contained, discussed in hushed meetings of scientists, generals, and politicians. But leaks would trickle out. Journalists would catch hints. And then, all at once, the announcement would appear across every channel, every feed, every phone in the world. An asteroid is on a collision course with Earth. Impact expected in less than a year. The first reactions would be disbelief. Some would think it a hoax. Others would demand proof. But as images were released, as orbits were published and confirmed by independent observatories, the reality would sink in. The entire planet would share a countdown, a date circled, not on one calendar, but on billions. For the first time in human history, every nation, every community, every person would face the same deadline. If the object were small, a few hundred meters across, it would still be catastrophic. Such a rock could destroy a city, a region, even a small country. Its energy would dwarf nuclear weapons. In that case, evacuation would be the priority. Scientists could predict the impact zone with some accuracy. Millions would be moved. Refugee camps would spring up. Supply lines would be stretched thin, but there would at least be a chance to minimize casualties. Cities would be abandoned, entire regions turned into ghost landscapes, all in the hope that lives could be saved by distance. But if the object were larger, a kilometer wide or more, there would be no safe zone. The impact would not be local, but global. It would not matter if you lived in the strike zone or half a world away. Dust and ash would be lofted into the stratosphere, spreading around the globe in weeks, blotting out the sun. Crops would fail, temperatures would plunge, oceans would acidify, famine and collapse would follow. Months of warning would not be enough to prevent it. Evacuation would save no one. Survival would depend not on where you lived, but on what preparations had been made. In desperation, some might propose nuclear solutions. The idea is seductive. Launch warheads, strike the asteroid, push it off course. But physics is not forgiving. With only months, building and launching such missions would be nearly impossible. Even if achieved, the chances of success would be slim. Worse, a poorly executed blast could shatter the asteroid into fragments, each still massive enough to hit Earth, turning one catastrophe into many. It would be a gamble, a last roll of the dice, undertaken because there was nothing else left to try. Meanwhile, societies would struggle with the knowledge of the countdown. Markets might collapse within days. Governments could impose martial law to control panic. Religion and superstition would surge, people searching for meaning in the face of cosmic indifference. Some would deny the threat, calling it a conspiracy. Others would retreat into fatalism, but many would try to prepare, building shelters, stockpiling food, fortifying seed banks, creating underground farms lit with artificial light. Scientists would scramble to preserve data, storing knowledge in hardened vaults, in the hope that if some survived, they would not have to start again from nothing. The human story would fracture. Some would act with selfishness, hoarding resources, retreating into isolation. Others would act with solidarity, pooling efforts, sharing what little time and knowledge remained. Families would gather, people would leave cities to be with loved ones, and children would ask questions no parent could answer. The awareness of a fixed, immovable end would change everything about how people lived those final months. And then the day would come. The asteroid would appear first as a point of light brighter than any star, growing larger night by night. In the final hours, it would blaze in the sky, a fireball brighter than the sun. The sound would follow a roar across the atmosphere, shock waves that rippled around the globe. At the point of impact, land or ocean would erupt, mountains would crumble, seas would rise as tsunamis tore across coastlines, forests and cities would ignite. Millions would die in moments, but the worst would come after. The dust would spread into the sky, dimming the sun, cooling the earth. Crops would wither in the fields. Winters would stretch across summers. Hunger would become the greatest enemy. Disease would follow famine. Civilization, already shaken by panic, would fracture under the weight of scarcity. The survivors would not be those with the most wealth or the most power, but those with resilience, ingenuity, and luck. Communities with underground food systems, with seed stores, with the ability to cooperate might endure. Those that fell to chaos might not. The difference between early warning and late warning could not be sharper. Decades of notice would mean calm planning, carefully designed deflection, safety achieved with precision. Months of notice would mean panic, desperate improvisation, and survival by chance. The dinosaurs had no warning at all. If our warning came too late, our difference from them would shrink. We might endure in pockets, but the cost would be staggering. And so this scenario, grim as it is, carries a message. It is why astronomers sweep the skies, why telescopes catalog faint dots, why space agencies plan missions to test deflection. It is not just science, it is defense. Because one day, another rock will come. Maybe not in our lives, maybe not for centuries, but inevitably, one will. If we see it early, we can act with confidence. If we see it late, we can only endure. The sky does not forgive lateness. The clock starts the moment the orbit is confirmed. The warning that comes too late is the nightmare we hope never to face. But it is also the lesson that drives us to prepare, to watch, to act before the countdown begins. Chapter 10. Surviving local strikes. Not every rock that falls from the sky is world-ending. Most of the time, what threatens us are not the planet killers like Chicxulub, but the smaller impacts. The ones big enough to devastate a city, a region, or a nation, yet too small to collapse all of civilization. These are the strikes that could happen in our lifetime, the kind that history has already given us glimpses of. To ask if we could survive them is to imagine what happens when the sky delivers disaster on a scale, both terrifying and survivable. We have already seen previews. In 1908, over the remote forests of Siberia, a rock about 50 meters wide exploded in the atmosphere. The Tunguska event flattened 2,000 square kilometers of trees. The shockwave circled the globe. Had it arrived hours later, the target would not have been wilderness, but St. Petersburg. Millions could have died. In 2013, a smaller rock, 20 meters across, detonated above Chelyabinsk in Russia. The shockwave shattered windows and injured more than 1,000 people. That object was never detected before it arrived. These are reminders that local strikes are not rare in geological time. They are not extinction events, but they are catastrophes measured in cities and lives. So what if one were detected today? Suppose astronomers spotted a rock 100 meters across, with a trajectory pointing toward Earth 6 months from now. The first step would be predicting the impact zone. Modern calculations can narrow it down with surprising accuracy. A path would be drawn across maps, and within weeks we would know where it would land. That strip of geography would become the most studied ground on the planet. Governments would begin planning evacuations. Populations would be moved. Highways would jam, trains would fill, airports would overflow as millions tried to escape. For the first time in history, entire cities might be abandoned in advance of a strike. The preparations would not stop there. Emergency stockpiles of food, water, and medicine would be rushed into shelters outside the predicted zone. Military and rescue teams would stand by to move in as soon as conditions allowed. Hospitals would be braced for casualties. Organizations would stage supplies across borders. It would be one of the largest coordinated efforts ever attempted by humanity, a global migration sparked by a rock from the sky. When the day came, the sight would be apocalyptic. The asteroid would blaze through the atmosphere, a fireball brighter than the sun, trailing a shockwave of heat and light. It would strike with the energy of thousands of nuclear bombs. The impact zone itself would be annihilated. Buildings, forests, rivers, everything in the immediate radius would vanish in an instant. The shockwave would flatten structures for hundreds of kilometers. Fires would spread in all directions. For those who stayed behind by choice, by chance, or by inability to leave, survival would be almost impossible. But for those outside the strike zone, survival would depend on distance and preparation. Air would be filled with dust, but not on the scale of a global winter. Skies would darken, but not for years. Crops might fail locally, but agriculture as a whole would endure. Unlike Chicxulub, the world would not end. It would bend, it would grieve, but it would recover. The challenge would be humanitarian. Millions displaced, cities destroyed, economies fractured. The survivors would face not extinction, but rebuilding. There's comfort in this. A city-killer asteroid is terrible, but it is not the end of humanity. We have the capacity to relocate populations, to provide aid, to absorb refugees into other regions. The Earth is vast, and most of it would remain untouched. The damage would be horrifying, but localized. Survival would not only be possible, it would be likely. Humanity, as a species, would endure. Yet there is also a warning. These events are more probable than the great extinction-level strikes. Tunguska-sized rocks arrive every few centuries, Chelyabinsk-sized rocks every few decades. A 100-meter asteroid could appear in any century. And while the planet would survive, the loss of a major city, or even several, would ripple across the globe. Imagine New York erased. Imagine Tokyo, or Mumbai, or Lagos. The shock to the world's economy, culture, and psyche would last for generations. Surviving local strikes, then, is not only about evacuating impact zones, it is about planning for the aftermath. It means having food reserves to bridge the gap after harvests fail. It means international cooperation to house millions displaced overnight. It means protecting knowledge, infrastructure, and stability, so that rebuilding can begin quickly. The asteroid itself would be the spark, but the test of humanity would come after the fireball faded, in the long years of recovery. And perhaps this is where our greatest strength lies. Unlike the dinosaurs, we can anticipate. We can run drills, build shelters, design response plans. We can move people before the impact, saving lives by foresight rather than luck. We have satellites, communication networks, and global institutions that can coordinate across continents. A local strike would be devastating, but it would not be a mystery. We would see it coming, and that vision could make the difference between chaos and survival. The truth is that we are vulnerable, but we are also adaptable. Local strikes remind us of fragility, but they also remind us of resilience. We can lose cities and still go on. We can rebuild homes, restart economies, regrow fields. A strike of this scale would scar the Earth, but it would not erase us. The lesson is sobering but not hopeless. Survival is not guaranteed, but it is possible. And in the case of local impacts, it is probable. The sky may one day drop another Tunguska, another Chelyabinsk, another unnamed rock big enough to destroy, but not to end. If it does, humanity will face grief and loss, but also the chance to prove its resilience. The test will not be whether we can avoid the fireball. The test will be what we do after. Chapter 11. Surviving Global Strikes. When people imagine an asteroid impact, many think of a blazing fireball tearing through the sky, followed by a single colossal explosion that leaves behind a crater. That image is not wrong, but it is incomplete. The most dangerous part of a global strike is not the initial impact itself, terrible though it would be, but the chain of consequences that unfolds across the entire planet in the years that follow. A strike from an object more than a kilometer wide is not a local disaster measured in cities or even countries, but a planetary event that alters climate, poisons oceans, and disrupts every food chain that depends on sunlight. Such an impact would test not only our ability to survive the blast, but our capacity to endure in a world fundamentally changed. Imagine a rock, 1 or 2 kilometers across, racing through space at more than 20 kilometers per second. The energy it carries is beyond any human scale, equivalent to millions of nuclear warheads detonating in an instant. On the day it strikes, the shockwave would level everything within hundreds of kilometers. Earthquakes would ripple through continents, tsunamis would sweep across oceans, and firestorms would ignite as molten fragments rained down. Entire regions would be erased in minutes, leaving behind not just a scar but a wound in the planet's surface. Yet even that would not be the true disaster. The real catastrophe would rise into the sky. The impact would hurl dust, ash, and vaporized rock high into the atmosphere, injecting particles into the stratosphere, where rain cannot easily wash them out. For months and even years they would linger, spreading around the globe, dimming the sunlight that warms the Earth. The world would not go dark in an instant, but each day would grow colder, dimmer, less fertile. Crops in the fields would wither, forests would weaken, and plankton in the oceans would die off as photosynthesis slowed. This is the scenario scientists call an impact winter, a sudden and prolonged cooling of the planet that turns fertile lands into barren ones and places humanity in a struggle not against the rock itself, but against hunger and cold. The collapse of agriculture would be swift. Grains such as wheat, rice, and corn, which form the foundation of diets for billions, require sunlight and stable seasons. Without them, harvests would fail across continents. Livestock would starve as feed disappeared, and with them would vanish another source of food. Oceans would suffer too, as reduced sunlight and chemical disruption killed plankton, the base of marine food webs. Fish stocks would plummet, adding to the crisis. Within months, food shortages would sweep the planet. Within a year, famine would become universal. Even nations with deep reserves would discover how quickly those reserves can vanish when billions of mouths need feeding. The question then is not whether civilization could continue unchanged, but whether it could endure in fragments. Humanity's survival would depend on preparation. Hydroponic systems capable of growing food under artificial light would become lifelines. Underground shelters stocked with supplies, equipped with generators, and designed for long-term habitation could sustain communities. Renewable energy sources such as nuclear or geothermal would be essential, because sunlight-dependent solar power would falter in a dust-choked sky. Seed banks like the one already built in Sethelbard would safeguard biodiversity, waiting for the day when fields could once again be planted. Survival would not be comfortable or widespread, but it would be possible in pockets of foresight and resilience. Yet such survival would not be evenly distributed. Wealthier nations would have the resources to build extensive shelters, while poorer nations might struggle even to move populations out of immediate danger zones. Inequality, already present in our world, would be magnified under crisis. Decisions about who enters shelters, who has access to limited supplies, and who must fend for themselves, would shape not only survival, but the moral legacy of humanity. The challenge of surviving a global strike would not be solely technological. It would be social, political, and ethical. History offers us faint analogs. When Mount Tambora erupted in 1815, the volcanic ash released into the atmosphere cooled the planet, leading to what became known as the year without a summer. Crops failed across Europe and North America. Famine spread, and millions suffered. That was caused by a single volcanic eruption. A kilometer-wide asteroid impact would release vastly more material, prolonging darkness for years rather than months. If one volcano could produce global food shortages, what would an asteroid do? The comparison shows us how fragile our food systems are, how easily disrupted by shifts in climate. And yet humanity possesses something no previous species has ever had: technology capable of creating alternatives. In controlled environments, crops can be grown without sunlight. Bacteria can be engineered to produce protein. Algae can be cultivated in sealed vats to generate calories when farmland lies barren. These methods are not yet widespread, but they exist, and in crisis they could be scaled up, becoming the difference between extinction and endurance. The dinosaurs perished because they could not adapt their food sources to darkness. We might survive because we can, but survival would also require cooperation. A global strike would make clear that no nation is an island. Dust would not respect borders. Famine would not stop at checkpoints. The temptation to hoard resources, to fight wars over dwindling supplies, would be strong. Yet only by sharing knowledge, distributing food where it is most needed, and preserving the infrastructure of global cooperation, would humanity have the best chance. The survivors of a global strike would be those who chose to work together, not those who retreated into isolation. Civilization would likely contract. Megacities that cannot be fed without imports might collapse. Populations might disperse into smaller, more sustainable communities built around shelters and controlled food production. The vast networks that sustain modern life, shipping routes, global markets, international trade, might fragment. But fragments can survive. If knowledge is preserved, if seeds and skills are passed down, the foundation of recovery can be laid even during the long years of winter. Recovery itself would come slowly. Dust and ash eventually settle. Sunlight would return, though perhaps after decades. Forests would regrow. Rivers would cleanse themselves, and the earth, as it always has, would heal. What remained of humanity would emerge into a world altered but fertile once again. Whether that remnant would rebuild advanced civilization or struggle in primitive conditions would depend on how well we prepared before the impact and how wisely we acted during it. So could humanity survive a global strike? The answer is yes, but not easily, and not without enormous loss. Billions could die in the famine that follows, but millions could live if shelters are stocked, if food production is reimagined, if cooperation triumphs over chaos. Unlike the dinosaurs, we know the risk exists. We can see the rocks in the sky. We can model the impacts, and we can build the systems to endure them. That knowledge is our advantage. To survive a global strike is to accept that we are fragile yet adaptable. That permanence is an illusion, yet resilience is a truth. The rock would fall, the sky would darken, the world would shake, and much of what we know would vanish. But if we prepare, if we cooperate, if we endure the long winter, there could still be survivors waiting to see the day when sunlight returns. Chapter 12. Human Resilience. When we speak of asteroids and impacts, the story often turns quickly toward devastation. Fireballs blazing through the atmosphere, shockwaves flattening forests, famine stretching across continents, and winters that linger long after the skies have darkened. These images are powerful because they are real possibilities. They remind us of Chicxulub, of Tunguska, of Chelyabinsk. Yet if we dwell only on destruction, we miss another story, one just as real, one just as important. That story is human resilience. For billions of years, Earth has been struck by rocks from space. The planet bears the scars, craters scattered across continents, scars visible even from orbit, silent reminders of ancient violence. Life has always endured those blows. After Chicxulub, when 75% of species vanished, survivors remained. Crocodiles hid in rivers, birds, small feathered dinosaurs, scavenged and endured. Mammals, tiny and nocturnal, burrowed through the darkness, eating roots, seeds and insects. Life bent, but did not break. From those survivors, the modern world emerged. Human resilience belongs to that same lineage. We are here because of countless acts of survival, countless adaptations by creatures who faced disaster and endured. Our resilience, however, is not only biological. Unlike the dinosaurs, unlike the ammonites, we have foresight and memory. We can see the rocks in the sky before they fall. We can recall the lessons of famine, war, and catastrophe. Resilience is not just the ability to endure impact, but the ability to prepare for it, to adapt in advance, to imagine futures and build for them before they arrive. That imagination is what sets us apart. Consider famine. In the past, when crops failed, millions died. Droughts brought kingdoms to ruin. Harvest failures sparked revolutions. But each disaster also left behind lessons. Irrigation systems were developed. Storage methods were improved. Trade networks expanded to move food from surplus to scarcity. Humanity learned to smooth the edges of nature's unpredictability. An impact winter would test us in the same way, but on a larger scale, and the same resilience that allowed civilizations to endure past crises would be called upon again. Technology extends that resilience further. Where the dinosaurs had no escape from darkened skies, we can grow food under artificial lights. Hydroponic systems allow plants to flourish without soil. Vertical farms stacked in warehouses can produce vegetables in climates where fields lie barren. Algae and bacteria, cultivated in vats, can provide proteins and fats when livestock cannot be sustained. These technologies are not yet global in scale, but they exist, and in a time of crisis, they could expand rapidly. Human resilience is not limited to instinct. It is amplified by invention. Resilience also lives in our social fabric. Throughout history, disasters have revealed both the worst and the best in humanity. Wars have been fought over scarce resources, yet cooperation has also flourished. After earthquakes, strangers pull one another from rubble. After tsunamis, nations send aid across oceans. Survival is rarely solitary. It is shared. If an asteroid darkened our skies, the test of resilience would not be only how individuals endured hunger and cold, but how communities held together. Would we share food with our neighbors, or hoard it behind locked doors? Would nations guard their seed vaults, or open them to the world? Human resilience is as much about trust as it is about strength. Even culture is part of resilience. When societies collapse, what often survives are stories, songs, and knowledge passed by word of mouth. Those fragments become the seeds of recovery. In an impact winter, books stored in libraries, data saved in servers, lessons taught to children in bunkers would matter as much as food and shelter. To survive is not only to keep bodies alive, but to keep ideas alive, to ensure that the knowledge of agriculture, medicine, and engineering does not vanish in the dark. Our ability to record and transmit knowledge across generations is one of the greatest shields we possess. It is easy to imagine resilience as strength, as unbending endurance, but often resilience is flexibility. The tree that survives the storm is the one that bends without breaking. Humanity's resilience may lie in our ability to change quickly, to shift from one way of living to another when circumstances demand it. In an impact scenario, that might mean abandoning cities that cannot be fed, turning sports arenas into hydroponic farms, or repurposing subway tunnels as shelters. Resilience is improvisation under pressure, and humans have practiced it for millennia. There is another layer still. Resilience is not only about surviving the immediate crisis, but about finding meaning afterward. Survivors of past wars and disasters often describe resilience as the ability to keep living when everything seems lost, to find purpose in rebuilding. After a global strike, survivors might ask what is worth saving and how should we rebuild. Choices made in that period would define the next age of humanity. Would we rebuild the same fragile systems or create ones designed to withstand future shocks? The asteroid would not just test resilience in survival, but in renewal. When we compare ourselves to the dinosaurs, it is tempting to think they were doomed and we are not. But that is too simple. Dinosaurs were powerful and well adapted. They fell because they lacked foresight. We are vulnerable, but we see the danger coming. That difference does not guarantee survival, but it gives us the chance to earn it. Human resilience is not invincibility. It is the fragile but real possibility that faced with disaster we can prepare, adapt, endure, and rebuild. So when we ask whether we could survive if a meteor fell again, the answer lies not only in telescopes and rockets, but in resilience. In the ability to imagine the worst and plan for it, in the willingness to cooperate in crisis, in the determination to keep knowledge alive when the sky grows dark. We have inherited resilience from every ancestor that endured droughts, winters, and famines. We have extended it with technology, with culture, with foresight. That is what makes the difference between extinction and survival. If a global strike were to happen, the Earth itself would not care. The planet would go on. Life, in some form, would continue. The question is whether we would be part of it. Human resilience is the answer to that question. It is the shield we hold, imperfect but real, against the indifference of the cosmos. Chapter 13. Technology as our shield. When we think of asteroids, the image that often comes first is one of inevitability. A rock hurtling toward Earth at unimaginable speed, unstoppable and indifferent. For most of Earth's history, that has been the truth. Dinosaurs could not see the asteroid that ended their reign, and no creature before us ever had a chance to even understand the danger. But humanity is different. We have built telescopes to find these wandering rocks. We have built spacecraft to reach them. And most importantly, we have built technology that can alter their course. For the first time in the history of life on Earth, a species has the means to shield itself from the sky. Technology as our shield does not begin with rockets or nuclear warheads. It begins with awareness. Radar systems, space-based infrared telescopes, and sky surveys track tens of thousands of near-Earth objects. Computers predict their orbits decades, even centuries ahead, calculating where and when they will pass. The simple act of knowing what is out there is the first layer of defense. The dinosaurs had no such luxury. For us, each asteroid cataloged is one less unknown, one less surprise. But awareness alone is not enough. At some point, we may have to act. The most straightforward method is the kinetic impactor, the very approach NASA tested in 2022 with the DART mission. A spacecraft no larger than a vending machine was launched across millions of kilometers of space and deliberately crashed into a small asteroid called Dimorphos. The goal was not destruction, but a subtle nudge. By altering Dimorphos's orbit around its parent asteroid, Didymos, scientists proved that even a small push, delivered with precision, could shift the path of a rock in space. This was a watershed moment in planetary defense, the demonstration that humanity can, in principle, move a celestial body. Another method is known as the gravity tractor. In this concept, a spacecraft would fly alongside a threatening asteroid for years, using its own small but constant gravitational pull to tug the rock ever so slightly. Over decades, this tiny influence could add up to a massive change in trajectory. Unlike a sudden impact, The gravity tractor offers precision and control, a way of slowly guiding an asteroid onto a safe path. It requires patience and foresight, but if warning comes early, it could be one of the most reliable defenses. There are more ambitious ideas as well. Some scientists propose painting an asteroid white or attaching reflective material to its surface. By changing how it absorbs and radiates heat from the sun, they could exploit the Yarkovsky effect, a subtle force that pushes objects through space as they re-emit solar energy. Over time, this small push could alter the asteroid's orbit. Others suggest deploying massive solar sails or focused lasers to achieve a similar result. These methods are futuristic, but they reveal the creativity of human defense. Where evolution gave dinosaurs teeth and claws, humanity has equations, machines, and imagination. And then there's the most dramatic option: nuclear devices. Contrary to the visions of science fiction, the goal would not be to shatter an asteroid into fragments, a dangerous strategy that could turn one impact into many. Instead, a nuclear blast near the surface could vaporize part of the rock, creating a jet of material that pushes the asteroid aside. It is risky, and it comes with political and technical challenges, but in a scenario where time is short, it may be the only chance left. For that reason, it remains on the table, studied carefully even as we hope never to need it. All these methods share one requirement: time. With decades of warning, a gentle nudge is enough. With years of warning, stronger pushes may still work. But with months, no technology we currently possess could stop a large asteroid. The shield of technology, then, is only as strong as our ability to see danger early. That is why the work of detection is as vital as the work of deflection. Telescopes and surveys are the eyes that give our shield meaning. Technology also protects in other ways. Simulations model how impacts would unfold, guiding evacuation plans and disaster preparation. Satellites track not only asteroids, but the dust and debris they leave behind, mapping hazards long before they become threats. Underground labs and seed banks safeguard the genetic diversity of crops. Nuclear plants and renewable energy systems could power underground farms during an impact winter. Each of these is part of the shield, not against the rock itself, but against the cascade of consequences it would unleash. Perhaps the most profound aspect of this shield is symbolic. Technology reminds us that we are not powerless. For billions of years, life had no defense against cosmic accidents. Now, for the first time, we can imagine a future where extinction is not inevitable. The very act of testing DART, of striking Dimorphos and shifting its orbit, changed more than the path of a rock. It changed the path of human possibility. It proved that survival is not only about luck, but about choice. Still, the shield is fragile. Funding can falter. Telescopes can fail. International cooperation, essential for planetary defense, can weaken under political strain. The danger is real, but so too is the temptation to look away, to dismiss it as too rare, too distant. Resilience, then, depends not only on the tools we build, but on the will to keep building them. Year after year, even when the sky looks empty. Technology is our shield, but like any shield, it must be held steady. It must be tested, improved, and ready before the blow arrives. For when the next asteroid is found on a collision course, the time for invention will be over. The only shield we will have is the one we prepared in advance. Chapter 14. Life after the dust clears. The day of the impact would be remembered as the beginning, not the end. The fireball would fade, the shock waves would settle, the tsunamis would recede, and in time the dust that blotted out the sun would begin to fall. After years of twilight, after the cold grip of an impact winter, the skies would slowly lighten. For the survivors who endured, who waited in bunkers and shelters, who tended to crops under artificial lights, the moment of sunlight's return would be one of awe and grief all at once. It would be a moment of renewal, but also a reminder of everything that had been lost. Life after the dust clears would not be the same as life before. Forests that once stretched across continents might be gone, reduced to charred remains. Grasslands might have withered under months without sunlight. Oceans, shaken by tsunamis and choked with ash, would still be turbulent and scarred. Yet life is resilient, and green shoots would appear sooner than expected. Mosses and lichens, hardy plants that can endure cold and low light, would spread first across barren soil. Insects, small and adaptable, would follow. Rivers would carve new paths. Lakes would form in impact craters, and slowly ecosystems would awaken. For humans, the sight of the first new growth would carry a weight of hope. It would mean that Earth was healing, but for survivors, healing the planet would not be enough. Civilizations shattered by famine and collapse would need to rebuild themselves from fragments. Some communities might have preserved their technology, maintaining power and agriculture even in the dark. Others might have fallen back to subsistence, relying on whatever scraps they could find. When sunlight returned, those differences would shape the new world. Groups that had preserved seed banks could begin planting again. Fields long dormant could be tilled, watered, and sown. Crops would return, though slowly, and the first harvest after the dust cleared would be celebrated like no harvest before. The return of sunlight would not instantly erase the hardship. Climate systems, disturbed by the impact, might remain unstable for decades. Rainfall could shift unpredictably. Storms could rage with new intensity, and winters might linger longer than before. Adaptation would be crucial. Farmers would have to learn new patterns, new crops, new ways of working with a changed climate. Some lands that once fed millions might become barren, while other lands, previously inhospitable, might bloom. Humanity would face a new geography of survival, shaped by the scars of the asteroid. Socially, the return of light would be a test of unity. During the darkness, survival might have been possible only in small, isolated groups. Communication networks could have collapsed, borders might have hardened, and distrust might have grown. But as the dust cleared, contact between groups would resume. Survivors would meet survivors, and decisions would have to be made to cooperate and rebuild together, or to compete for the fertile lands that remain. History suggests both would occur. Wars might be fought over water and farmland, but alliances might also form to share knowledge, resources, and hope. The story of humanity after the dust clears would depend not only on the planet's recovery, but on ours. Technology would play a vital role. Communities that preserved renewable energy, that maintained libraries and data vaults, that trained engineers and doctors, would become centers of recovery. They would be the seeds from which civilization could regrow. Those without such resources might lag behind, struggling in more primitive conditions. Inequality, sharpened by the disaster, would not vanish with the return of sunlight. If anything, it might widen. The challenge would be to bridge those divides, to spread knowledge and technology widely enough that humanity as a whole could rise, not just a few isolated groups. And yet, there is reason to believe we could rise. After every collapse in history, from the fall of Rome to the aftermath of world wars, humanity has rebuilt, often stronger than before. The difference after an impact would be the scale, but not the principle. Survivors would gather, trade would resume, cities would be founded again, and slowly the rhythms of civilization would return. They would carry with them the memory of the impact, the stories of the years of darkness, and that memory could guide them to rebuild differently, perhaps more cautiously, perhaps more sustainably, perhaps with greater awareness of the fragility of life under the sky. The planet itself would carry scars. Craters would remain for millions of years, silent monuments to the disaster. Some might fill with water, becoming lakes, while others would stand as barren circles of shattered rock. But around them, life would flourish again. Birds would nest in the trees that returned. Fish would swim in the lakes, and humans might build villages along their edges. What was once destruction would become part of the landscape of a renewed Earth. Culturally, the impact would become myth. Survivors would tell stories of the day the sky fell, of the years without sunlight, of the struggles and sacrifices. Future generations might grow up, hearing those stories not as science, but as legend, lessons about humility before the cosmos. Yet for those who kept records, who preserved data and knowledge, the history would remain, clear and detailed, a warning to prepare for the next time. Because there will be a next time. The sky will always hold rocks, and Earth will always be in their path. The question will be whether the memory of survival is strong enough to keep our defenses ready. Life after the dust clears is a vision of resilience. It is not a return to what was, but the beginning of what could be. The Earth would renew itself. Slowly, painfully, beautifully. Humanity would rebuild differently, but enduringly. And the story would shift from catastrophe to recovery, from loss to adaptation, from darkness to light. The rock would leave its mark forever, but the world that grew after could be shaped not only by what was destroyed, but by what was learned. So if the sky falls again, and if we endure the long winter, life after the dust clears will not simply be survival. It will be the chance to start anew, to remember how fragile we are, to honor the resilience that carried us through, and to build a world worthy of that survival. Chapter 15. A shared responsibility. When we think of asteroids, we often imagine them as distant, solitary rocks drifting through the void, mindless and indifferent. Yet if one of them is ever found on a path toward Earth, its arrival will not be the responsibility of any one nation, one government, or one people. It will be a global threat, and the only answer will be a global response. A meteor does not care about borders. It does not respect politics, ideology, or wealth. The impact zone might be Asia, or Africa, or North America, but the consequences will ripple across oceans and hemispheres. That is why survival depends not on what one country can do alone, but on whether humanity as a whole can recognize the truth. Defending Earth from the sky is a shared responsibility. This responsibility begins with detection. The telescopes that scan the heavens, the satellites that track faint objects, the computers that calculate orbits. They belong to agencies spread across continents. NASA operates them in the United States. ESA coordinates in Europe. Other programs exist in Japan, China, South America, and Africa. Each sees part of the sky, but no one sees all of it. Only by sharing data do scientists form a complete picture. The rock that threatens Earth could emerge from any direction, hidden in the glare of the sun, or emerging from the dark beyond Jupiter. If every nation hoards its discoveries, blind spots remain. But when nations share, the blind spots shrink. Knowledge itself is the first act of responsibility, and it must be shared freely. Responsibility also lies in preparation. If a dangerous asteroid is found, who builds the mission to stop it? Who funds the rockets, the spacecraft, the navigation systems? No single country has unlimited resources. Even the most powerful space agencies rely on collaboration for complex missions. The International Space Station floats in orbit today because nations set aside rivalry long enough to cooperate. A planetary defense mission would demand the same spirit, magnified many times. It would require pooled funding, pooled expertise, pooled effort. It would require trust that the survival of all outweighs the advantage of any. The challenge is not only technical but political. In a world where nations compete for influence, power, and resources, asking for cooperation on an existential scale is difficult. Some governments may resist, reluctant to share sensitive technologies. Others may argue over who leads and who follows. Yet the asteroid will not wait for treaties to be signed or rivalries to be resolved. Its countdown will continue, day by day. Shared responsibility means acting despite politics, because the alternative is to let division weaken us until it is too late. Beyond governments, shared responsibility extends to humanity as a whole. If an impact occurred without warning, or if evacuation became necessary, the burden of survival would fall unevenly. Wealthy nations could shelter their people more effectively. Poorer nations might struggle. Without cooperation, billions could be abandoned. With cooperation, resources could be distributed more fairly. Aid could be directed where it is most needed, and humanity could survive together rather than fracture apart. Shared responsibility means refusing to let survival be determined solely by wealth or geography. It means acknowledging that the value of life is not measured by borders. Even preparation for the aftermath is shared. If the skies darken, if famine spreads, if civilization trembles, recovery will require international solidarity. Seed banks in one country must serve farmers across the world. Energy grids must be repaired with materials sourced from many nations. Scientists must share knowledge without hoarding it. For prestige, shared responsibility is not only about stopping the asteroid before it hits, it is also about helping one another after it strikes. There are precedents for this kind of cooperation. After natural disasters, nations send aid across oceans. After disease outbreaks, medical knowledge is shared rapidly, sometimes saving millions. After wars, reconstruction has been supported by international coalitions. These moments prove that humanity can rise above division when the need is undeniable. The difference with asteroids is scale. The need will be planetary, the stakes ultimate. Shared responsibility will no longer be optional, it will be the only path to survival. This responsibility is not limited to governments or institutions. Ordinary people carry it too. Public support for space agencies matters. Funding for research depends on citizens understanding why it is necessary. If the danger feels abstract, distant, or irrelevant, the shield weakens. Shared responsibility means educating, inspiring, and reminding humanity that the sky is not always safe, and that preparing for it is as essential as preparing for storms, earthquakes, or floods. A culture of awareness strengthens resilience, and that culture must be shared across all of humanity. Ultimately, a meteor strike is a reminder that Earth itself is shared. We may divide it into nations, but the planet is one body, moving through the same cosmic sea. An asteroid large enough to endanger us is a force that treats us as what we truly are, a single species living on a fragile world. Shared responsibility means embracing that perspective. It means understanding that the boundaries we fight over on maps vanish when viewed from space. It means realizing that survival requires not walls but bridges. If a rock is ever found on a collision course with Earth, the story of our survival will not be about the brilliance of one nation or the heroism of one leader. It will be about whether humanity as a whole accepted responsibility for itself. Did we share knowledge openly? Did we pool resources fairly? Did we see beyond politics and borders long enough to act as one? If the answer is yes, survival is possible. If the answer is no, then our greatest threat may not be the asteroid, but ourselves. Shared responsibility, then, is not just a strategy. It is a moral truth. It is the recognition that the sky belongs to no one, that its dangers threaten us all, and that its defense must be collective. If we can hold to that truth, if we can act on it, then perhaps when the next rock comes, humanity will meet it not as scattered nations, but as one planet standing together beneath the stars. Chapter 16. Looking up. Looking forward. When we speak of meteors, asteroids, and the possibility of another great strike, the conversation often tilts toward fear. We imagine the fireball tearing through the sky, the shockwaves flattening cities, the famine that follows, and the desperate struggle for survival. These images are vivid because they are possible. They are reminders that Earth is not sealed off from the cosmos, but is part of it, vulnerable to its accidents and its violence. Yet, when we look forward, the story does not have to be only one of dread. The same sky that holds danger also holds opportunity. To look up is not simply to search for threats, but also to search for meaning, to see the place of humanity in the universe, and to recognize the responsibility that comes with that vision. Looking forward begins with vigilance. The simple act of watching the skies, night after night, telescope after telescope, is itself a declaration of hope. It is the refusal to let fate be blind. Each faint dot tracked across the stars, each orbit calculated, each database updated, is a statement that humanity does not intend to be surprised. To look forward is to accept that impacts are inevitable on geological timescales, but that extinction need not be. The dinosaurs had no warning. We do. To look forward means to keep the watch unbroken, generation after generation. It also means preparation. Detection alone will not save us. If a rock is found decades in advance, it must be met with action. Missions like DART have proven that we can, in principle, alter the orbit of an asteroid. That principle must become practice, with systems built, tested, and ready long before the need arrives. Preparation means building spacecraft, not as prototypes, but as defenses. It means funding research not for prestige, but for survival. It means treating planetary defense as infrastructure, as essential as medicine, as agriculture, as water. To look forward is to see defense not as science fiction, but as responsibility. Looking forward also requires imagination. The threat of impact is real, but it is only one part of the cosmic story. The same telescopes that search for asteroids also discover galaxies. The same spacecraft that could deflect a rock could also explore new worlds. By building tools to defend ourselves, we also build tools to expand ourselves. Humanity's shield can also be its wings. The act of looking up, of preparing for asteroids, is part of the larger story of exploration. It is the same instinct that drives us to walk on the moon, to send probes to the outer planets, to dream of Mars. To look forward is not only to fear what comes from the sky, but to embrace it, to step into the wider cosmos with knowledge and care. Responsibility will remain at the center. The danger of asteroids is shared, and so is the duty to prepare. No nation can watch the entire sky alone. No nation can fund or launch every mission alone. The survival of the species depends on cooperation. Looking forward means looking beyond borders, seeing Earth as one planet, one home, one fragile sphere moving through the dark. It means building systems of trust that allow data, technology, and resources to flow where they are needed most. It means refusing to let rivalry blind us to the greater truth that in the eyes of the cosmos, humanity is one. But looking forward also means humility. The universe is vast. The rocks that wander through it are countless. Our technology is strong, but not perfect. Even with vigilance, even with preparation, we cannot guarantee safety forever. To look forward honestly is to admit our vulnerability, yet humility does not mean despair. It means recognizing that survival is fragile and precious. It means cherishing the present even as we prepare for the future. It means teaching our children that the sky above is not only beautiful but also alive, full of forces that can change history, and that awareness is the first step toward endurance. Life after a strike, should one ever occur, would demand resilience. Communities would rebuild, knowledge would be preserved, seeds would be planted again, and humanity would rise from the shadow of disaster. That possibility is part of looking forward too. The belief that even if the worst comes, it will not be the end. We can endure, we can adapt, we can carry memory forward into light. Resilience is part of the human story, and it will remain part of our future. And yet, the greatest vision of looking forward is not survival, but flourishing. Imagine a world where planetary defense is not an emergency project, but a foundation of civilization, where space agencies share their discoveries freely, where new telescopes map the heavens in exquisite detail, where spacecraft wait in readiness to deflect any threat. Imagine that world, and then imagine how much more it could do. With that knowledge, with that technology, with that cooperation, humanity could not only survive but thrive, exploring the solar system, harvesting its resources, learning its secrets. Looking forward is the beginning of that journey. So when we ask if humanity could survive if a meteor fell again, the answer is yes, not because the danger is small, not because the challenge is easy, but because resilience, imagination, and cooperation give us a chance. The fire may fall, the dust may rise, the world may darken, but survival is possible if we prepare, if we act, if we share the burden of responsibility. Looking forward means understanding that possibility, carrying it with us, and choosing to act on it before the countdown begins. To look up is to see danger, but it is also to see beauty. It is to see the Milky Way stretched across the night, to watch shooting stars scatter through the atmosphere, to glimpse planets glowing softly against the dark. It is to understand that the same sky that holds destruction also holds wonder. Looking up reminds us that we are small, but looking forward reminds us that small is not the same as powerless. Humanity cannot stop the universe from moving, but we can shape how we meet it. Life on Earth has endured extinction before. Entire dynasties of creatures have vanished beneath falling skies. But life has always returned, and humanity now holds the knowledge to ensure that we are not just another chapter in that long story of endings. Looking forward, we can choose a different path, one of vigilance, preparation, imagination, humility, and resilience. The sky will always hold rocks. The earth will always be in their path. But whether those rocks define our ending or our endurance is no longer only a matter of fate. It is a matter of choice.